Hey guys, this is part 2 of that video. If you haven't watched part 1 yet for some reason, then you should go back to part 1, because this will make more sense. Okay, example 2 is where we are in the packet right now. And the first thing that we're going to try and understand in this question is, what does it mean to add two vectors, right? We just looked at in example 1, decomposing a vector, right? Saying Joe's velocity consisted of this and this, right? Okay, because he was crossing the street and also going down the street. So he had really, if you want to think about it that way, two different velocities. Okay, because it had components. Now what we're going to do is add together two vectors. Okay, now the way this is going to look in your homework might sometimes be like this. We'll say A plus B. That means add together those two vectors, and the little arrow over top of it means that it's a vector. All right. On the other hand, you might also see subtraction of two vectors. All right, and if they ask you to subtract a vector, that's actually no big deal. It's not really any different. So we'll get to what if we were subtracting these two vectors in a minute. The other thing that you might see is they'll put an absolute value sign around it, which is actually not that crazy of a thing. When you see the absolute value signs, absolute value tells you how far something is from zero, right? So it ignores, is it this way, is it that way? It's just how far is it from zero. In other words, you could say it's the magnitude of its displacement from the origin. That's what these things here mean. They just mean what is the magnitude of A minus B. So if you figure out what A minus B is, then you're going to get what is the magnitude of that vector. If you're not sure what that means just yet, that's okay. I'm going to explain how you find the magnitude of a vector in a moment, if you're not quite sure what that's all about. Okay, so let's first deal with what does it visually look like when we're talking about adding two vectors. Sometimes it's maybe a little bit hard to appreciate visually what it means. So let's just imagine that these two vectors, A and B, that they gave you in example 2, happen to be displacement vectors, right? And so obviously you can't walk in two directions at once, right? But if you're like following directions or something, it might say, okay, now walk 5 miles north, then walk 3 miles east, right? Okay, and so in that case you might say go north and then east. Okay, or you could also have gone east, and then north. That would have worked too. You'd probably get there as long as there weren't like buildings in the way. Or again, if there weren't buildings in the way, you could maybe have gone straight there. But the idea of adding together these two vectors is that you do one, then the other. The way that you always draw vectors when you're adding them is actually not usually like this. This is an awkward way to draw vector addition. It's usually going to be head to tail is the way that they say it. So like if you're saying go north, then east, there's your go north vector. Here is now our go east vector. You would not draw go east with the arrowhead ending where this one is, right? The tail of the next arrow picks up where the head of the other one was. All right, so visually, we're now going to represent what this is. That's what those two blank graphs are for. Let me hold that up in case you're not sure. Look, right here, these ones. We are going to draw addition of those two vectors two different ways. All right, here it goes. Let's say that we do A first. So we're like Boy Scouts following directions, and our compass says we have to go 5 miles at 60 degrees north of east. That's actually what it kind of says in the text, right? This vector is 5 units long, and this is 60 degrees. All right, so on the first blank one, you would draw this. Here's our origin, right? All right, and then we follow vector B. Oh, that's not right. Not quite, anyway. Okay, so then the total, the sum of those two vectors is where we end up, which is right here. I should have picked a third color for that. Let me get a third color. Ooh, it's a black mark. That's not a very straight line, but you'll just have to deal with it, guys, okay? All right, so if I go this way and then that way from where I end up right there. Let's suppose we add those vectors in a different order. This can now be on your third blank graph. Let's suppose that we follow vector B first, which is 5 miles at 30 degrees south of east. Here goes. 30 degrees south of east. Now, all right. And if I drew everything to scale, it would be easy to see that those two vectors are, the sum of those two vectors, rather, is of the same. Okay, let me draw it on top of this one in case you don't quite believe me. Here's my blue one. Here's my red one. And so they land in the same place. Hey, look at that, it's a parallelogram. Okay, there you go. All right, fine. Visually then, that's what vector addition is. All right, also visually, if we said we were doing, instead of A plus B, we were saying A minus B. A minus B would be do A as said, and then you would flip the direction of that one. Instead of adding it, you would subtract it. You'd go up the other way. So visually, that's what vector subtraction is. Okay, now let's do the next part of that question. It says that we are supposed to, part B now, express A and B in unit vector notation. Okay, so that means the I and J stuff. All right, let me erase this. And for a moment here, let's just look at vector A. Just vector A. Let's ignore B for a moment. Here's vector A. Kind of, right? All right, it has components. All right, it has an X component. Let's call that X component, since this is vector A, we'll call its X component AX. And here's its Y component, AY. All right, if you think back to what we did a minute ago where we decomposed the velocity of Joe, and also previous to that when we looked at, okay, we've got an R vector at an angle of theta, right, and it has an X and a Y component, we would find this one using what trig function? Oh, wait. You go ahead, you figured out what trig function. Just kidding, I don't have that much time. No, I'm limited for time on the video because this thing will cut me off. That's why I had to do it in 2 parts instead of one very long video. So here goes. What trig function relates to the adjacent side? Cosine. If you said cosine out loud, then you are a model citizen. Good job. I don't have cookies. I couldn't give you cookies. This is a video. Anyway, so it's A cosine theta is going to be the X component. All right, when we say A, we mean how long is this vector? 5 was the answer, so 5 cosine 60 degrees. That's going to be 1.5. Right, maybe it's meters, I don't know, whatever. It doesn't say what the units are, so but it's 1.5 is the X component of A. All right, now this one. The Y component of A is going to be proportional to the what trig function? Very good. It's proportional to the sine component. So A sine of theta. All right, 5 sine of 60 is going to be 4.33. I did that in my head. Actually, I didn't. I lied. I already had it worked out. Okay, so that means that vector A is this. Here's vector A. In unit vector notation, 1.5 I plus 4.33 j. All right, now what I would like everybody to do real quick, you can pause the video for a minute while this happens, is do the same thing, but do it for B, right? Find the components of B. All right, so pause the video for like about a minute. Everybody figure out the components of B. Pause the video, right? Right. Okay, let's do it then. You found the components of B. Good job. They are. Whoops, not AX. I mean B. BX, all right, and BY. And this angle, it says, is 30 degrees. So you should have come up with BX is 5 times cosine of 30, which is going to be 4.33. All right? And then BY, the length of that side is, I'm sorry, I have a mistake, and if you notice it, good job. This is not 1.5. That is completely bogus. 2.5. Ha! You thought you were going to catch me. You thought I was going to come back after the weekend and you'd make fun of me for making a mistake in a video, didn't you? Yeah. All right, so BY is 2.5. Again, like using the sine function. All right? Okay, now that's how long that side is. But actually, when I go to write down what vector B is, here's what I would write. The x component is to the right. So that one would be exactly what I wrote here, 4.33 I. But if you look at the y component of A is going up. The y component of B is going not up, right? Going down. In other words, it's going the opposite direction. So it needs to have the opposite sign. BY is actually going to be minus 2.5 j. Okay, now I want to add these two vectors together. And this is the super easy part because we're all very good at addition and subtraction. Your i's add, your j's add. So when I add these two together, I'm going to get 6.83 I, and then this one's going to be plus 1.8, maybe, yes, 1.83 j. All right, so there that is. All right, fine. What does that answer mean? Now, the way that it was phrased in the prompt, it said was find vector C, which is the sum of those two vectors. So this is now a new vector that we get to call C. So we would say vector C equals that stuff right there. What is vector C? Vector C is that third vector that we drew a minute ago on our diagrams, right? When we did, here was A, here was B. The sum of those two, this side, that's vector C. Okay, so there we have it. That's vector C written in unit vector notation. So that is what vector C is. That's this direction here, right? That magnitude and direction, written as unit vector notation. All right, now part C of this question is going to ask you what is the magnitude of C. All right, now if you think back a moment ago to when we did Joe's velocity, the magnitude of Joe's velocity was 3. It's the hypotenuse. The magnitude of A is 5. The magnitude of B was also 5. So that means the magnitude of C is the hypotenuse of this triangle, which is 7.07. All right, I'm about to get cut off. See if you can figure out what trig function to use there, and then check the answer in your notes packet, which are in your Google Drive. All right, homework should be good.